Hello, my name is Sean Conway, and I'm a graduate student in cognitive psychology at the University of Massachusetts Amherst. This is a pre-recorded presentation for the 2022 meeting of the Society for Mathematical Psychology. I'm going to be talking about categorization with multiple items, empirical and modeling results. This is work that I conducted along with my advisor, Andrew Cohen. This work is based around the idea that while considerable progress has been made studying categorization decisions in which a single stimulus needs to be classified into one of several categories, for example, is this rodent a gerbil or a hamster, categorization decisions can also be framed as one in which someone needs to choose the best category member from a set of multiple options. For example, which of these job candidates seems most likely to fit in well at our workplace. In addition, research in decision-making has demonstrated that choice can be affected by the set of options presented. Our research also considers how the choice set affects category decisions. We've conducted a few experiments and work is still ongoing, but I'm going to present results from a two-dimensional categorization experiment using simple perceptual stimuli that we call turtles. The turtles vary on the angle of the yellow arc and the radius of the green half circle. The category members are sampled from a bivariate normal distribution shown on the left, while non-category members are sampled from a bivariate uniform distribution over the entire stimulus space. The first part of the experiment, the learning phase, shown on the right, took part in 200 trials where participants saw a single stimulus at a time and decided whether or not each stimulus belongs in the category with a simple yes/no response. They were provided with feedback after each trial. Half of the trials consisted of category members and half consisted of non-category members. After learning came the transfer phase. During this phase, participants chose the most likely category members from a set of 2 or 3 options on each trial. Part of this experiment tested the attraction effect, in which people are more likely to choose one of 2 equally good options if a weaker, more similar option is presented along with the set. In the 2 squares on the top left, we show 2 example attraction effect trials. The target is labeled with a T, the competitor with a C, and the decoy with a D. The target and competitor are equally likely category members, but the decoy, which is dominated by, but more similar to, the target, should push participants who select the target more often. The attraction effect trials are split into types that we call 180 and 90, named because the target and decoy are 180 and 90 degrees apart from each other, respectively. This effect violates independence of irrelevant alternatives, or IIA, an axiom satisfied by the well-known loose choice rule, which is assumed by, for example, the generalized context model, a very successful model of categorization. We show an example attraction effect trial on the right. Target, competitor, and decoy are labeled here, though these labels were not present in the experiment. There were 2 other types of trials: easy trials, in which a single option was clearly a better option than the others, and sampled trials, in which stimuli were directly sampled from the distributions during the experiment. We modeled transfer data by extending random utility models, a well-known class of models from the choice literature, using principles from the GCM. Random utility models predict the probability that an option is selected from a set based on each item's utility. In this case, utility is a function of the item's category similarity. We fit the models to individual subject data using maximum likelihood estimation. We fit all trials for each subject rather than just attraction effect trials. We incorporate parameters from the GCM, such as psychological sensitivity and dimension weighting, as well as choice set dependent parameters, such as bias for intermediate options, like the middle stimulus in this figure, as well as a parameter that boosts a similar dominant option, like the target in the attraction effect trials. We also incorporate variance-weighted dimension weights. That is, in certain cases, dimension weights were not estimated, but rather calculated dynamically based on the variance of each dimension in a given choice set. For example, in the choice set on the right, the variance for angle is far greater than the variance for radius, which is virtually non-existent, so the model will treat the angle dimension as more important for this particular choice. Importantly, the model uses Loose's choice rule. Without the bias parameters, the model will satisfy IIA. Though we did find a small attraction effect only the 180 attraction effect trials, there was considerable variability across participants. While the model with the attraction effect parameters and the model with the intermediate bias parameters, not shown here, best account for these data, model comparisons based on Bayesian information criterion show that the simple models, where dimension weights were either fixed at equal attention or based on the variance of the choice set, tended to be preferred over the more complex models. On the right, the fits for the simple models show that while these models handle the sample data well and do okay on the attraction effect trials, they have trouble accounting for some individual subject variability. While IIA is violated in certain cases, by and large, a simple model that assumes IIA tends to be preferred. Thank you for listening.